So this video is about metathesis reactions, which are double replacement reactions involving ionic compounds in aqueous solutions, but this also covers acid-base reactions. These reactions are all not redox reactions, so nothing is changing its oxidation number during the process. We'll deal with redox separately, and redox will involve combustion reactions, synthesis reactions, decompositions, and single replacements, and we'll cover those later in the year. So essentially what we look for is an insoluble precipitate, which will be what happens in an AP question that you're going to see. So when AgNO3 reacts with barium chloride, we normally get, the ions are going to separate. So you can have Ag plus NO3 minus plus barium 2 plus 2 Cl minuses, arrow, and on the other side you're going to have, you're looking for a solid. So you've got the AgCl is going to precipitate out as a solid, and the barium ions, okay, and the nitrate ions are going to sit around, and what we end up getting is an equation. Now we could balance this by putting a 2 here, but we'd have to put a 2 here as well. The main point, however, is this: in the end, the nitrates are here and here, the bariums are here and here. Those ions really aren't reacting. They're considered to be spectator ions. So we kind of just ignore them because they're not really reacting. At the end of the reaction, we're going to form this solid precipitate, and the ions, the barium and nitrate ions, are still hanging out, just floating around. Now the concentration might change during the course of the reaction, but the actual number of moles or millimoles of those ions respectively will be unchanged. So we get a final net ionic reaction of Ag plus Cl minus gives us AgCl, because we want the smallest whole number ratio. And this is our net ionic reaction. Now, I rarely see them make anybody write this whole thing out like this, but it's plausible that they could, so that they show you understand that some things disassociate. Now, you can get lots of these net ionic reactions, but the critical thing is to look at your final formula for getting the final net ionic reaction. So for this one, let's say you get 3 K pluses plus 1 phosphate plus copper. Now this is plus 2 because it's with 2 nitrates, and it's not going to change its charge because it's a metathesis reaction. And you got these 2 nitrates, and you put the arrow, and you look to see, will anything precipitate out? And in fact, K pluses, all 3 of them, were never going to precipitate out because group 1s are always soluble. The nitrates are never going to precipitate out because they're always soluble, right? I'll put the 2 in front to make it look good. All right. Now on the other side, we got to figure out the formula for the copper phosphate, so a copper 2 phosphate, right? So we're going to get a precipitate of CuPO4. The charge of this is -3. The charge of this is +2. So we're going to get to neutralize this, we need 3 plus 2 coppers to balance like the 2 -3 phosphates. So we end up with a. Let me just do some erasing of these charges so it's not so confusing. All right. Put the drawback on. So we end up with Cu3 parentheses PO42. So our net ionic reaction, again, now we have to put the numbers. We need 3 coppers, right? So we have to have a 3 up there, right, to make right. Plus 2 phosphates gives us a Cu3 parentheses PO4 close parentheses 2. Now this is primarily what we're going to use when we do our stoichiometry. Okay, and so that we're going to be very careful. Like if we have, right, we're going to have to figure out how many moles. This is the important thing. We're going to have to figure out, how many moles of copper ions we have, or how many moles of phosphate we have when we do these chemical reactions. Okay, to do the stoichiometry. All right. Acid-base metathesis reactions are a little bit different, and you're going to see why, because in particular when we're dealing with a weak acid versus a strong acid. For a weak acid that completely ionizes when it goes into the water, right, so this is going to be like aqueous because it's not an acid unless it is in water, right, and this guy is going to be in water as well, you basically have H plus Cl minus, right, plus Na plus OH minus gives you this. Now what happens is the H plus and the OH minus come together and make water, and that's a molecular substance, right? And even though this water consists of an H plus and an OH minus, a hydronium and hydroxide coming together, it's not the exact same formula, so it's not going to cancel out. The Na plus will still be there, and the Cl minus will still be there just hanging out, and they cross out, And what you end up getting here is your standard neutralization equation, which is H plus OH minus gives you H2O. Now this will be the net ionic, but only when you're dealing with a strong acid with a strong base. And there's lots of weak bases and lots of weak acids. For example, this is acetic acid or vinegar. I use this example a lot because we have a lot of vinegar, or maybe I just like salads. Either way, it's one of the more common ones that shows up in lots of examples. And I want to illustrate the point here. Since acetic acid, only about 1 in 10,000 molecules, and I'll talk about how we quantify that later, will actually ionize, we can't rewrite this thing as anything other than a full molecule. So we write this like so, Na plus OH minus. Now, like all acid-base reactions, we're still going to make water and the salt. So what's going to happen is we're going to make water, H2O, right? And we're going to make sodium acetate. Now these two guys here really are still separate because that's a still soluble. So really it should be a plus. Let's look at the plus there and the minus there, right? And they're still separate. So I'm going to erase this and rewrite this the proper way, right? Since they're not really together, we just write Na plus C2H3O2 minus. And in this case, the only things that really cancel out are the sodiums. So the net ionic for a weak acid with a strong base like sodium hydroxide is basically you keep the original acid in there like so. The sodium ions kind of disappear as spectators. Okay, the base, the hydroxide, okay, reacts with the acid to produce the water, and that stays. And we have some acetate ions floating around as well. And since the acetate ions aren't on the other side, and what this tells you something, when you're done with this, unless you completely react this, you're still going to have some of those acetic acid molecules still around. Well, actually, I shouldn't say that. We'll get back to that later. It depends on how much you actually add. So, my mistake, but I don't feel like re-recording. Okay? We will now talk in the next video about limiting reagent problems in solution chemistry.